So in this video, we're going to show you the substitution method for solving systems of linear equations. This is one of the two algebraic methods that can be used to solve systems of equations. We previously showed you the graphing method, and one of the disadvantages of the graphing method is its accuracy. What if the two lines meet in the middle of a box of one of those grids in the rectangular coordinate system? Then it would be challenging to tell exactly where that point was. So we need to introduce you to some algebraic methods, and we're going to start with the substitution method. Here's what you're going to do. Notice I put a little T table here. It's going to help us out. And on the left side of the table, you're going to look at your two equations, and you're going to find one that's solved for one of the variables if possible. So notice that our first equation is already in slope-intercept forms, and it's solved for the variable y. So that equation is going to be written on the left-hand side. So again, you look at the two equations that are given, and if you have one that's solved for one of the variables, use it on the left side of this T table. Okay? Then the second equation gets written on the right side. So I'm going to write that here on the right-hand side. Because this equation on the left is already solved for y, we're ready to go to the substitution step. And that is where we take this side of the equation. See how it says that y is equal to negative 2x minus 4? We're going to take that and substitute that expression on the right for the y variable in that second equation that's in the right side of the t. So it's going to look like this. You've got your 3x minus 2, but where the y is, you're going to put a parentheses, and we're going to replace that y with the negative 2x minus 4 from the equation that's on the left side of the chart. See that? And then just the rest of it stays the same, minus 6. So now notice what's happened here on the right-hand side. You have an equation now that is entirely in x, so that means you can solve. So the first step we're going to do is we're going to go ahead and distribute this negative 2. So we get 3x plus 4x plus 8. Pay special attention to those signs. And then we're going to go ahead here and combine like terms. See what we're doing there. And now we're going to isolate x, so we'll subtract 8. We get 7x equals negative 14, and then divide by 7, and we get that x equals negative 2. So now we've used the right side of the chart to find x, but we're not done because we know that these two lines meet at an order pair that has a y value too. So we need to still solve for y. So now you're going to take this x equals negative 2 back over to the left-hand side, and you're going to substitute it in the x there. So now you're going to get y equals negative 2, and then your negative 2 from the x that you just found here on the right-hand side, minus 4. Okay, so notice how we use the x that we just solved for on the right, but we put it in the equation on the left. And now, why did we do that? Look, it's already solved for y, so it makes it kind of easy. So we have 4 minus 4. Oh, looks like y is 0. All right, now, when you go to check this, since we used the equation on the left-hand side to solve for y, and that's the latest thing we did, go ahead and check on the right. So I'm going to check over here. So I'm going to come back to the right, and then I have 3x, so 3 times negative 2, minus 2 times the y, which was 0. And notice that that does give us negative 6 equals negative 6, so that checks. So what did we just find? We found that these two lines, the solution, they meet at the point negative 2, 0. So that means that we have a consistent system because we have a solution, and that the lines are independent. They're not the same line. So we have one point of intersection, which is at the order pair negative 2, 0. All right, example number 2, we once again have here two equations, two linear equations. But notice this time that our first equation is not in slope-intercept form. It is solved for the variable x, but that's okay. We still have an equation that's solved for one of the variables, so we're going to use that on that left side of that little T chart thing here, this T table. And then we're going to write the second equation on the right-hand side. So that's your first step, just deciding which equation goes on which side. And then On the left side, we already have this equation solved for x, so we're going to take this piece of the equation, the one that says 3y minus 9, and we're going to come to the right-hand side, and it's going to replace the x there, okay? Because remember, this is x, right? That's what this says over here on the left, that x is 3y minus 9. So we're going to replace it for the x on the right. Don't forget to put parentheses. Okay, so here's my equation. And then in that parentheses where x was, I'm now going to substitute 3y minus 9 in for x. That's why it's called substitution method. All right, well, we're ready now here to solve for y. So we're going to distribute. We get 6y minus 18 plus 5y equals 4. And we're going to add those like terms on the left. So 11y minus 18 equals 4. And then we're going to add 18 to both sides so that we can isolate y. So 11y equals 22. And then we're going to divide by 11. And that gives us that y equals 2. So we've now solved for the y value of the point of intersection. We need the x, don't we? So we're not done. So we're going to take this value of y and bring it back to the left and substitute it up there. So we get x equals 3, and then the y was 2. We just found that, minus 9. So 6 minus 9 for x equals negative 3. Now we're going to check our answer. We're going to bring it back over to the right-hand side, and we are going to write 2 times x plus 5 times our y, and we're going to see if we get that 4. And so negative 6 plus 10, that does equal 4. So this checks. So our solution is an order pair again, negative 3, 2. That's our solution, and we once again have a consistent independent system, one point of intersection. Now, in this next example, notice that both of these equations are in standard form. So we don't have one of the equations that is solved for one, either x or y. So we're going to have to do a little bit more work. However, there is one equation where we have the variable x with a coefficient of 1. Do you notice that? That's a tip. You want to pick the equation that would be the easiest to solve for either x or y. And so that second equation would not be too tough to solve for x. The second equation is going to come here on the left-hand side, and then the first equation will be the equation we use on the right-hand side of our table that we've got going here. Now, in the left, we have one extra step this time. We have to solve for x. Solve for x first, because we really need to solve for one of the variables. X is the easiest. So we're going to subtract 3y and put it with the 12. So now we have x equals negative 3y plus 12. And what are we going to do? We're going to take this piece right here, and we're going to substitute it on the right-hand side where the x is. So we have negative 2, and then we're going to have our negative 3y plus 12 that we got from the left side of the t-table. And then we have plus 3y equals 3. So now we distribute here the negative 2, and we get 6y minus 24 plus 3y equals 3. And so here we get 9y minus 24 equals 3. Then we're going to add 24 to both sides so that we can isolate our y. So 9y equals 27, and dividing by 9 we get y equals 3. And then we're going to take that y value across to the left-hand side so we can solve for x. So we get x equals negative 3 times our y, which is 3, plus 12. And so we get x equals negative 9 plus 12, or x equals 3. And we're going to check. We're going to bring this over to the right-hand side to check. And we have negative 2 times x is 3, plus 3 times 3, which is our y. Does that equal 3? And we get negative 6 plus 9 equals 3. And so 3 equals 3. So that really checks. So our point of intersection is 3, 3. That's our solution. And what kind of system do we have? Consistent, independent again. Those are the two lines that cross at one point of intersection. 3, 3. All right, problem number 4. We're going to take a look at these two equations, and we're looking for one of the variables to have a coefficient of 1. Do you see it? It's in the first equation, isn't it? This y by itself right here. Okay, so that means that we're going to use the first equation on the left side of our table, and then we're going to use the second equation on the right side of our table. And now over here on the left, we're going to solve for y. So y is going to be 2x minus 4. And we're going to take that 2x minus 4 and come across to the second equation and substitute it where the y is. So now we're going to have 2x plus 3, and then here comes our substitution from the left, equals 12. Now we're going to solve for x, so we will distribute the 3. So 2x plus 6x minus 12 equals 12. And then we combine like terms here for an 8x and add the 12, so we get 8x equals 24. And then we're going to divide by 8, so x equals 3, which we're going to bring across to the left-hand side and substitute it in for the x. So we have y equals 2 times 3 minus 4, or 6 minus 4, or 2, which we're now going to bring across to the right for a check. 2 times x, which is 3, plus 3 times y, which is 2. Does that equal 12? And 6 plus 6 is 12. Awesome, so that checks. So what's our solution? Our solution is the order pair 3, 2. And what kind of system do we have? Consistent, independent. Are you starting to get the idea? Okay, we've got these last two. Okay, as we look at these two equations, which equation should we put on the left-hand side? If you said the first, you're right. Why? Because the y has a coefficient of 1, right? Okay, good. If you notice that, you're on your way. So put it on the left-hand side, and then on the right-hand side, we're going to put the second equation. Just write it up here. Okay, very good. And now on the left-hand side, we have to solve for that y, so we're going to subtract the 2x, and then we're going to take that right-hand side here, and it gets substituted for the y. So we have negative 8x minus 4, and you're going to put a parenthesis here, and then you're going to put your substitution, negative 2x plus 6 equals negative 24. And now we're going to solve for x, so we're going to distribute the negative 4 here. So we get negative 8x plus 8x minus 24 equals negative 24. And now we're going to add these like terms here, and what happened there? Did you notice that we got 0x? Did you notice that our variable is gone? Uh-oh. So anytime that you're solving algebraically for point of intersection between two linear equations and your variable cancels like that, it drops out, it ends up being 0, then you have one of our two special cases. Do you remember what those were? We had one case where we had two parallel lines, so there was no solution. They never met. And then we have the second case where we have the fact that the two lines are the same line, represent the same line, the same graph, and then we have infinite number of solutions. So how you know which case you have here is you're going to read this remaining statement. Negative 24 equals negative 24. Is this true or false? And if you said true, you're right. A true statement. So that tells you that you have here the case in which the two lines are the same line. So you get infinite number of solutions. What do we call that system? Well, we call it a consistent system with dependent lines. Okay, again, these are the two lines that lie one on top of the other. The graphs are the same line. And so the solution to the system is that we have an infinite number of them. And if all the order pairs that are on the line satisfy the system, and there's an infinite number of points on the line, we call that a consistent dependent system. In this next problem, which equation shall we use on the left-hand side? Which will be the easiest one to solve for one of the variables? If you said this second one, solve for x, you're absolutely right. So we're going to use that one on the left. And then we're going to use the top equation. It's going to come here on the right-hand side. Again, we're going to solve for that x here. Notice again, sometimes my students will want to solve for y because they're used to putting lines in slope-intercept form. However, I want you to notice that if I solve for y here instead of x, then I would have to divide by 3 and I would get a fraction. And I don't know about you, but if I can avoid fractions, that's not a bad thing. So always look for the variable that has either a 1 or a -1 coefficient, and that would be our x. So that's why I'm solving for x here rather than solving for y. Okay, and then we're going to take this expression and we're going to substitute it for the x on the right hand side there. So parentheses, as you know, for the substitution. And now we're going to solve for y. So we're going to distribute, and we get 6y minus 8 minus 6y equals 3. And then what do you notice is happening here with these like terms? It's looking like we got rid of our variable again. Notice no variable, but take a look at the remaining statement. -8 equals 3. True or false? That's a false statement. So what does that say? Well, now we've got the parallel lines. There is no solution. These two lines will not meet. They're parallel. No solution to the system. And this is the inconsistent system. Parallel lines.